In this fourth video of Module 7, Groundwater Modeling, I'll walk you through a technical report on a groundwater model for Vashon Maury Island. This is a competently executed report accomplished under timelines and budget dictated by a sponsoring agency, King County Regional Government. I want to emphasize that it is a quality report within the dictates of its budget and timeline. In my walkthrough, I will be emphasizing the flaws in the report, but remember, all groundwater models are intrinsically flawed. You need to acknowledge and recognize the nature of the flaws and then ask yourself the question whether, despite the flaws, there are robust conclusions that answer the questions posed in the process of deciding why a model was necessary in the first place. The learning goal is straightforward. Be familiar with the case study, the Vashon Maury Island groundwater model. Here's the cover page for the case study. This is a technical report. The sponsoring agency is King County Regional Government. The organization that prepared the report is DHI, Water and Environment. They're located in Portland. This is an international company. DHI stands for Danish Hydrologic Institute. It was initially centered in Denmark. Let's look at the overall structure of this technical report. The first chapter basically answers the question why a model is needed. The second chapter discusses what computer code is used to undertake the modeling, how the model was designed. The third chapter focuses on the data used in order to construct the model and how calibration was accomplished from the available data. There's also a sensitivity test discussed in the Chapter 3, the Model Calibration and Results section. Note, in this report there is no verification, i.e. there were no time-dependent data used to check the predictions of the model. The fourth chapter focuses on predictions. These are called scenarios. The scenarios involve both changes in climate and changes in development on the island, i.e. how many people and how many wells and how much water is needed. So the results are contained within Chapter 4. Chapter 5 focuses on the limitations and weaknesses of the model, and this is an appropriate thing to have in any groundwater model report, is to acknowledge the nature of problems and limitations in accomplishing the goals of the particular modeling exercise. Every technical report needs an executive summary. An executive summary needs to be essentially 1 page in length. In the first paragraph of this technical summary, the report identifies the context and reasons for constructing a groundwater model. The second paragraph of the executive summary summarizes what was done, what models were used, what data was incorporated in the models. The third paragraph focuses on predictions that the model provided, and the fourth paragraph has a discussion of implications based on the predictions. So this is a nice format, concise format that leads the reader through to understand the scope and objectives of this report. Let's focus on the goals and objectives as identified in the first chapter of the report. The goal was to build and maintain a model describing groundwater flow in the Vashon Maury Island area. An additional goal was to have a model that would allow sustainability issues to be addressed. And in order to accomplish a discussion of sustainability, you need both the model and the data, which is what's highlighted in the area under the blue here. And finally, they focus on the need to assess societal impact. And of course, if you're going to do this, you need to address how the information is going to be communicated. They provide a table of the computer models used in this particular exercise. These are all based on Danish Hydrologic Institute models. These are essentially the European equivalent to ModFlow, which is more commonly used in the United States. The modeling package include both models for surface processes and evapotranspiration, as well as for the flow of water in the subsurface. Let's walk down the list. The top module here, the Mike She OL, is for overland sheet flow, the water that just comes along the surface. There's a Mike 11, which includes streams and lake hydraulics. The flow within the unsaturated zone and evapotranspiration was taken part in the models labeled UZ and ET. Finally, the model for the groundwater is the Mike She SZ. This is a groundwater flow and storage model. It is a basic finite difference model. Finite difference as described in the previous module, previous video of this module, and so it is dividing the subsurface into blocks that are arranged in sheets and layers. Model construction. Well, they used LiDAR to define the surface. That's the topography of the surface. The model was set with a basic grid resolution of 500 feet. So the island was crisscrossed with lines at a spacing of 500 feet. Subsurface was informed by borehole log interpretations provided through the Pacific Northwest Center for Geologic Mapping at the University of Washington. These borehole log interpretations were accomplished in 2004. Like most studies in technical and science field, there's prior studies that are built on for the most recent version, and there is a ModFlow model for Vashon Island done by the United States Geologic Survey that precedes this study. And in this study, the uppermost units, the Vashon recessional deposits and the alluvium deposits, were handled as lenses rather than a continuous layer. And let's see, so the basic model for the groundwater was 8 layers and 1 lens, the lens representing the surface discontinuous layers of alluvium and recessional outwash. There are 4 aquatards within the model, as well as the deeper aquifers. Here's the basic layer cake structure of the model. The top layer is a lens. That means discontinuous pods of material. This is linked to the geologic unit known as Vashon recessional or quaternary Vashon recessional deposits. This surface layer is considered to be an aquifer, and it has very high hydraulic conductivity. And you notice that the horizontal conductivity is given a 10 times larger value than the or actually 100 times larger than the vertical conductivity. The topmost aquatard layer is the Vashon till. This has a much lower conductivity, and the vertical conductivity is much lower than the horizontal. Below the till is QVA, the Quaternary Vashon Advanced Outwash Deposits. This is the regionally extensive sand and gravel layers laid down in advance of the Fraser glaciation. This has a moderately high value for hydraulic conductivity. Again, the vertical is less than the horizontal. Below that is a layer labeled here as QPFF. PF stands for pre-Fraser. Pre-Fraser means deposits prior to the most recent glaciation. The final F stands for fine, as in very small grain size. The QPFF then is an aquitard with low hydraulic conductivity in horizontal and vertical directions. And layers 3 and 4 are both labeled QPFF. This is a artifice of modeling in which they needed to add 2 aquitard layers to the model in order for some numerical stability problems to be resolved. The layer below the QPFF is labeled QAC. This is no longer conforming to mapped geologic units. It's merely a convenience of identifying layers A, B, and C below the other units. And this A layer has final letter C standing for coarse, and coarse standing in for something that has more porosity and thus is an aquifer. Below the A layer is the B layer, which has fine grain size, and for these glacial fluvial sediments tends to be an aquitard with a low hydraulic conductivity. Below the BF layer is the BC layer, which is again an aquifer with coarse grain size and high hydraulic conductivity. And at the bottom of the pile is the QC layer, which is defined to be an aquitard. Thus we have 4 layers that are identified as aquifers. The lens, which is discontinuous at the surface. Layer 2, which is the regionally extensive outwash, advanced outwash deposits. And then deeper deposits, layer 5 and 7. Layer 5 is near sea level, layer 7 is below sea level. 4 aquitards separate the aquifers, and they're highlighted in green in this layer cake representation in the table. Now, recognize that Vashon Maury Island, it covers nearly 37 square miles. Having a 500-foot grid spacing allows for about 40,000 blocks in a single layer. With 8 layers in the model, that's 40,000 times 8 means there are 320,000 blocks within the model. Let's compare that structure in the model conceptualization with the actual known geology of Maury Vashon Island. Here's a cross-section running from north to south across Judd Creek, which is midway down the island. Note again that last letter F means fine and refers to a low hydraulic conductivity layer, whereas C corresponds to a high, larger grain size and larger conductivity. Now, let's see, so here are the mapped units. You have the recessional outwash, which is less than 15,000 years old. You have the Vashon Till, which is about 15,000 years old. Below the Vashon Till is the Vashon Outwash, which is about 15,000 years old. Then below that is the pre-Fraser glaciation deposits, which are something like 20,000 years old. Below that, there are drifts or deposits from prior glaciations going back 70, 80,000 years. There's a Whidbey Formation, which is over 100,000 years, and that then moves into prior glaciations. And Double Bluff is again part of prior glaciations, and then QHC is greater than 200,000 years old and move into still earlier glacial periods. On the map, you'll see that the recessional deposits show up as discontinuous pods, as highlighted in red in Judd Creek. The advanced till is fairly extensive across the island, and I've highlighted it on either side of Judd Creek, and you can see that it drapes across going down into the valley of Judd Creek, but is cut by the creek itself. Below the till is the QVA, our primary aquifer, and you'll see that QVA is thickest and continuous across this area. However, you'll notice quite large variations in its thickness, and you'll note also that Judd Creek intersects and cuts completely through it. Prior to QVA, we have the pre-Fraser glaciation, and in this cross-section you'll notice that they only show up as isolated pods. Below the QPF, you'll find quite a collection of glacial fluvial deposits which are not exactly in layer cake orientation. They're discontinuous, they have sloping interfaces. It is these layers, when they are fine, that are labeled aquitard, and when they are labeled with a C, they are possibly aquifers. So it's interesting to look at this picture and compare it with the layer cake of 8 layers illustrated on the previous PowerPoint slide. Let's talk about the boundary conditions. The current model uses a zero flux, no flow boundary condition around the perimeter of the model for all layers except for QVA and the QAC. So 2 aquifer layers have a flow out around the boundaries. In one case, the flow out is defined in terms of a fixed head boundary at about 125 feet above mean sea level. For the lower aquifer, the QAC, a fixed head of 23 feet was used. 23 feet means that the head is higher than mean sea level, so there is subsurface discharge from this aquifer into the Puget Sound. So, data to calibrate the model consisted of an overall water budget determined from streamflow hydrographs and precipitation monitoring, and then groundwater head observations in wells located across the island. Now, in the process of accomplishing the construction and calibration, they compared their simulated water budgets with those from previous studies, and the idea wasn't that they tried to match the previous estimates, but rather it was their method of gauging the reasonableness of their simulated values, and also to understand when their values were different from the prior models, why their values differed. So there's some uncertainty about how to match observations to their simplified model. In some cases, they found that the well depths suggested the wells were completed within the model confining unit, and given the wells were producing water, it was unlikely that the wells were completed in an aquitard, and thus they associated the well with the nearest aquifer either above or below the layer that was represented by the observation depth of the well. There are other simplifications in here, and they note the subjective process of associating observations with models. Calibration now. First of all, note that they used these definitions in determining values that are listed in the Table 8, which I'll show you in a minute. The groundwater recharge represents all the precipitation plus all the irrigation plus all the septic tank return minus the amount that was evapotranspired and minus the amount that ran off. Groundwater discharge was equal to the base flow to the stream plus all the pumping, plus all the stream flow, plus all the outflow to the sound, which occurred under the sound and not through any streams. And finally, groundwater recharge was the groundwater discharge plus or minus the change in storage that they observed in their model. So now let's talk about their calibration and their ability to match the model to actual data. So they note that the model does a good job in predicting the summer base flow conditions for Shingle Mill Creek, and the percent stream flow volume error is only 8%. However, during the rainy season, the model tends to over-predict base flow and under-predict peak flow. Additionally, the model simulates small runoff events in spring and late fall that do not appear in the observed data. So their overall volume error in the 3 years of simulation was about 30%. So they could not explain about 30% of the stream flow. Now, in the case of Judd Creek, they had much larger errors, and they note that the calibration is poor for Judd Creek. They overpredict summer base flow by 40-some%, and the rainy season base flow is underpredicted. Runoff events are severely underpredicted. The overall volume error for the 3-year is a underprediction of 41%. So they are failing to account for 41% of the water in these creeks. Now, the next is the calibration errors in comparison with the wells. Now, I'm going to describe how they quantify error. If you have 2 wells, and if the model predicts head low by 2 feet in one well and overpredicts by 2 feet in the other well, the mean error in their abbreviation, ME, is 0. So minus 2 feet plus 2 feet equals 0. That's, I think, a fairly strange way of describing the error. So a very large error in the negative direction can be compensated for in the mean error by a positive value. Now, the mean absolute error would be taking the absolute value, adding them together, and dividing by the number of observations. So if you have one that's 2 feet high and one that's 2 feet low, the mean absolute error is at 2 feet. The root mean square error is obtained by squaring the error and adding the squares and then taking the square root of that and dividing by the number of observations. And in this case, with 2 observations, one high and one low by 2 feet, the root mean square error is also 2 feet. So the paragraph from their document talks about mean errors, mean absolute errors, and they note that overall their mean absolute error is 19 feet. So on average, they mispredict the height of water in wells by about 19 feet. Here are the wells that they used for calibration. There are a total of 34 wells. Remember, this is 34 wells situated in 4 different aquifers. So divide 4 into 34 and you see that we have just a handful of measurements in each aquifer. In fact, the deepest aquifer has only 2 wells completed within that depth range. And the problem is both of those wells are fairly close together, so they do not sample the spatial distribution of the deep aquifer at all. Remember that the model is described in terms of values of hydraulic conductivity in 320,000 blocks, each measuring 500 feet on a side. You notice then that 34 observations is a fairly undersampled representation of properties of the aquifer across the island. Now, in these 34 wells, you'll notice that in the top layer, the QVA, the mean absolute error is about 24 feet. And this is an improvement over the earlier mod flow model, which had a mean absolute error of 39 feet. For the middle AC aquifer, the mean error in the new model is 10 feet compared to 25 feet in the older model. And for the deeper aquifer, it's 42 feet for the new model, and actually the mod flow model did better at 37 feet. So for all layers taken together, the mean absolute error is about 19 feet now, and for mod flow is 36 feet. On this basis, the authors of this report claim some victory in improving the misfit of the model to the data. So let's look at some overall results for the water budget of the island. And in Table 8, the authors compare their results, the Mike Shee model, with the mod flow model of the USGS in 2005, a groundwater management plan dated 1998, and the initial CAR report, which was accomplished in 1983. In each of these, the modeled precipitation differed. So let's look at the numbers as percent relative to the precipitation that they used in their model. So all models have 100% precipitation going in, and then all the other columns should appropriately add up to 100% of the water going somewhere. Looking to the far right in the CAR report, 44% of the water went out as evapotranspiration, and 33% of it went out as runoff in the various creeks. That allowed for an 11% groundwater recharge, and then 9% of the 11% returned as base flow to the streams, and 2% of the groundwater recharge exited via the aquifers under the Puget Sound. So that's the base comparison going forward to the Mike Shee report, in which you'll notice that runoff is 25%, so it's less than the CAR report. The Mike Shee report accounts for the irrigation and septic tank components of the water budget. The groundwater recharge in the Mike Shee report, though, is 31% of the total amount of precipitation, so significantly more water gets into the groundwater on the Mike Shee report. Notice also that much more of the water exits via outflow to the sound, 17% in the Mike Shee report compared to the 2% in the CAR report. In the Mike Shee report, you have a change in groundwater storage over the 3-year period of 2%. So now that there is a calibrated model that has been evaluated in the context of prior models, let's look at some of the model predictions. So their scenarios fall into two categories. There's future pumping scenarios, which involve adding population to the island and adding wells to full build-out. And the climate change scenarios, they used a model for global climate change that has been developed to predict temperatures and precipitations in the Puget Sound area at times in the future. Now, these predictions are run as scenarios and compared to the base model that was calibrated on current conditions. And for the 10 scenarios discussed, they looked at how base flow to Shingle Mill and Judd Creek changed, and you'll notice that the changes are really pretty insignificant on either build-out or climate change. They amount to a few percent of the base flow over the period. And since the model is incorrect to tens of percent on current values, then it seems as if the predicted changes are essentially negligible. So what are the summary of their results? Well, they note that their model agrees well with previous estimates, And they note that their prediction is that, let's see, this is the comparison of the absolute errors, and they notice that they've done a better job of fitting the wells than the previous models. And when they run their scenarios, they see a fraction of a foot to a few feet changes in hydraulic heads on the basis of climate change and on the basis of more development and larger populations on the island. Then the report goes into a discussion of uncertainties and limitations. And they brag that their estimations should be better than previous estimates because they modeled the relevant processes rather than making assumptions about what evapotranspiration should be. They note that their outflow of the Puget Sound is poorly constrained. That 17% that flows in, and it's difficult to do this. Well, they think it's more realistic, but the value is purely derived on the basis of calibration, and so calibration on 34 wells to constrain the properties of 320,000 blocks. They note that the runoff events and base flow are not very well handled, particularly for Judd Creek, and they try to postulate why they did so poorly on this. And they notice that, well, let's see, they may have underestimated the amount of impermeable ground. They may have used wrong precipitation values, since they used values of precipitation based on those measured at the Seattle-Tacoma International Airport. Let's see, they acknowledge that their calibrations are still quite high, as large as 30 to 40 feet in some locations, but they note that mod flow also had large errors at these locations, and that their model is better than mod flow. It's reduced those errors, and both models, being finite difference, may simply not be an accurate representation of the true geometry of the major deposits. Now, from our look at the geologic cross sections and how it's been simplified into 8 layers, I think that's a bit of an understatement. So in the next paragraph, they further note the inherent difficulties, and they say, representing the complex geometries of the glacial fluvial units in a finite difference model like mod flow or Mike Shee is challenging, I'd say nearly impossible, because of the constraints of needing to have grid cells of uniform dimension with constant upper and lower elevation, the inability to have spatially discontinuous model layers, and the numerical instabilities that occur when you have large changes in layer thicknesses over short distances further make the finite difference modeling, in this case, problematic. They also note that their constant head boundary condition for the Vashon outwash deposits, advanced outwash deposits, are problematic because you could have inflow of water from the air into the aquifer in order to maintain the constant head at these boundaries. And they note the interaction of the deeper layers with the Puget Sound is very difficult to represent. Well, they have no data whatsoever, and the amount of water that flows in the Puget Sound was determined strictly by calibration and by difference of water that they got out into the streams and springs. So it's very uncertain. The report was externally evaluated, and some fairly negative comments were made, and I'll just highlight some of these. There are fundamental simplifications in this computer model that seem to be far afield from the actual island situation. For example, the island's complex and discontinuous geologic layering is represented in the model as 3 simple hydrologically continuous water-bearing layers, which seems very inaccurate when compared to actual well logs. And this is a criticism you could launch at every single groundwater modeling activity. The illusion of accuracy given by the model report and predictions seems misleading and risky. That brings to the end my discussion of the case study of the Vashon Maury Island groundwater report for the King County Regional Government. That also concludes the videos for Module 7, Groundwater Modeling.